drawing electric field lines. Now, in our last lesson, we alluded to some of this in talking about uniform or constant electric fields and using F equals QE equals MA to problem solve some of our problems, but here we're going to introduce them formally, officially, and go into detail about how you will be able to draw the electric field lines outside of a source charge, and that's probably a good place to start. Electric field lines are generated by source charges, like Q source here is plus 16. Q source down here is negative 32. So how do we draw those 4 blue field lines? How do we draw those 8 red field lines? Well, the first thing we are going to do is utilize what are called test charges. Test charges by convention are positive. So never negative, they are by convention positive, and they are always infinitesimally small. The reason that they have to be infinitesimally small, and this is sometimes a multiple choice concepts question in test banks, is that we can't have the test charges themselves generate their own electric field that would then interfere or have to be added to the Q source in the problem. So you need to think of these test charges, positive first of all, and then as kind of pretend, right? Theoretical construct test charges where they're just going to be there to help us draw our field lines. All right, number 2. Well, number 2 says that we need to have a scale for our map. So just like a geographic scale has a map, like 1 inch equals 10 miles or whatever the scale is, our field line maps have scales, and our scale is based on the value of whatever the lowest charge will be in our field map. So here I chose a scale, and it's arbitrary, just like when you draw a map, you don't have to make 1 inch 10 miles. You can make half an inch 10 miles. It'll change just the zoom, the view of the map. But here I chose 1 line per 4 coulombs, right? So 1 line per 4 coulombs means I'm going to use 4 lines for my 16 coulombs, and what you want to do is put your field lines in the quadrants of the map, but not on axes. So you can see I have my 4 field lines here in the quadrants, but not on axes. Now, when I go to 32, 32 is twice 16, so I have to have twice the number of field lines. So you have to be consistent. The scale is arbitrary, but once it's chosen, if you're going to show other field maps on the same page next to each other, you have to be consistent. All right, number 3. Field lines begin on positive and end on negative. So if they gave me this field map, the 2 plates, and showed me the blue field lines, so draw those blue field lines in there, even if they didn't tell me that the left side was positive, I would know it's positive because the rule is electric fields begin, right? Begin on positive, end on negative. So even if they didn't tell me, I would know that that left plate is negative. And you can see this is consistent with our rules 1 and 2, because the positive source charge here, right, our positive source charge here pushes a positive test charge, so our field begins on positive, and somewhere out there in infinity we would say a negative exists, but if it's only a single source charge, we do not put in a negative out at infinity. And here we see our field lines end on negative, but we have a negative source charge like we have here. What you get is the negative attracts the positive test charge, and the field lines terminate on the negative. So everything's consistent. Okay, so we did talk about this a little bit in our last lesson, that the density, which is the spacing between the lines, so we're at number 4 now. The density, the spacing between the lines, gives us a very quick visual of what field is stronger and what is weaker. A weaker field has more widely spaced lines. A stronger field has more densely or closely spaced lines, and it is proportional. So if, for example, there was a 1 centimeter spacing between these electric field lines, and I measured and there was a 1/2 centimeter spacing over here, then it would be twice as strong. Number 5, field lines cannot cross. Why can't field lines cross? Because by convention, field lines always show the net electric field. The net electric field with F equals QE gives a net force. You cannot have two net forces acting on a single particle. So if we have a little q, that green would be the q that is in a region of space where some source charge is generating electric field. If field lines crossed, we would not know which one corresponded to E net. 6 I highlighted because that's important. We'll understand why, but even without thinking we need to know, no electric field inside of conductors ever for electrostatics. And let's see our polarization explanation below. So on your page, you see that no field is shown in the conductor box. Well, draw in that what nature is doing is allowing for polarization, what I call perfect polarization, so that when I take the external field and I add this internal field to it, we get 0 always inside of conductors. Now, dielectrics, insulators, we're going to see, will allow for some electric field to go through, but they are always what is called thinned, meaning more widely spaced. So on your page, make sure you get these 2 black lines in here showing that they are thinned. So we'll understand on another page of notes, so we don't need to go into great detail, but insulators have values that tell us about their properties, and this is called a dielectric constant. The dielectric constant tells us about the amount of polarization. So if K equals 2, then that is going to correspond to not 2, but 1/2 of the electric field from the original external field that gets produced inside. So here I showed 4 external fields, so I take half of that. If it were 8 field lines that I showed outside, I would show 4 inside. The last thing we need to know about our field maps is that in electrostatics, the electric field lines will always be normal, perpendicular to the surface of a conductor. Otherwise, if we allowed the external field to exist in this state, right, what we would see is that there's an E parallel. That E parallel, right, would allow electrons to flow along the surface of the conductor. Well, if electrons are flowing, that's a circuit, that's current, that's not electrostatics. Electrostatic means that the electric field has to be E external, must always be perpendicular. Always, always, always. So that's the actual E external. Okay, well, there you have an explanation of how field lines are drawn. We're definitely going to practice more with this, so you'll get a better feel for how to think through and analyze these types of situations yourself. But please go back and reference this page of notes anytime you are unsure about how to draw field lines.